Okay, so how you do this calculation is, maybe it looks difficult, but it's not very difficult. So what you do is you take the paths, and then each different bath or wash basin, whatever, has different instant water flow, and that's 0.3 for bath, 1.1 for basin, and then you check the. So what you do is you check the. You sum all these together. So in this case, for JKM and N, you do 0.6, 0.3, 0.1, plus 0.1, 0.1, and then you go to use this formula because it's B1, so use this one, so 0.682, and then you get this value. So 0.6 gives 0.40, and then you see that here in this one. So 0.6 gives 0.4, and then apparently it's a low speed because it's a branch derivation. I'm not really sure what that means, but apparently use 1.2. So this value is actually not correct. Well, I mean, maybe it's correct, but apparently we're supposed to simplify it. So all of these, we're going to use 1.2 instead. So then you go to the abacus, and then you have 1.2 like there. Oh yeah, all of them are based on 1.2, so that's good. 1.2, and then we said 0.4. So 0.4, 1.2, you draw a line, and then you see, it's pretty bit difficult to see, but here is the, this is the unitary loss of charge. And then here, 2.2 is the diameter. This is what we see here. And they do that for all of the elements, I guess. And then that's just for this part, the first part here. And then for the second part, you check, I'm not sure how many, I think this is probably correct, right? But you can see the 90-degree turns, and then you add this length, extra length together with the total normal length, which we have in the model. And then you just take the formula. So you take this one, unitary, times the length, plus the extra length for all the strange ones. They get this together. And that's cool. And you do that for all the stretches, I guess. So, what else do we need to know? I'm not sure right now what a branch derivation and column distributors are, but I guess the main idea is that the first floors or whatever that distributes all, that connect to all of these are the distributors. I mean, the makes sense. And what else? Then if we talk about one of the exercises we did was let's do another one. So the pump calculations, there are okay, maybe do it now. So the needed pressure, it's in one of the slides, is I'm not sure what that means, but in the exercise there was a ground floor and a 5-story building, and then also has a basement unit. So and also that has a pump, and the pump was 0.65, so 65 centimeters up. And then the HC, it's the height of the basement, plus, which is in the exercise, plus the floor slab, the thickness of the floor slab, plus 2.85, that's the height of the normal slab, plus the floor slabs, and there are 6 floors total, so there are 2.6 plus 0.3 plus 6 times that one minus the height of the pump itself, and that's 21.15. And if you add 0.65 plus 21 plus 15 is 21.8, and apparently you start out with between 20 and 30 water column things, and then you remove 30% of this value. So, or actually 20%, I guess. I don't know. Yeah, actually 20%. So, or it says 30%. Okay. whatever. So you take the P min finally is the height of the pump plus the total thing of the building plus 20% of that plus 10, which is the normal. I think the normal the tap. I think that's the. I mean, I know it's supposed to be for the tap, but I'm not sure. That's why I had 10. So in this case, it's 36.16. And the maximum is the P minimum plus 20. And because that's 56.16, that means that's over the limit of 50, which means that there is you have to reduce the pressure. Right? You have to have pressure reduction valves. And then for a pump thing, I haven't done that yet, but it's in the I'll get that later.